So this is 2D particle kinematics. Number 13. It says a person's capable of swimming 4.5 miles per hour across a 0.15 mile wide river. We did a problem pretty similar to this in class. Okay. So the river is moving 8 miles per hour. The river is 0.15 miles across. The person can swim 4.5 miles per hour. So that means that how fast can someone swim? If somebody treads water in a river that's going 100 miles an hour, they're moving 100 miles an hour, you know? So the speed that you swim is always relative to the water. So the velocity, if this is the coordinate system, the person is going to swim 0, 4.5, and that is the velocity of the person relative to the water. Okay. The velocity of the water relative to the ground is in the positive x direction, the way I drew it, at 8, 0. And we want the velocity of the person relative to the ground. So the relative motion setup is velocity of the person relative to the ground is equal to the velocity of the person relative to the water plus the velocity of the water relative to the ground. So this is equal to 0, 4.5 plus 8, 0. So 8, 4.5. And then you can use the constant acceleration equations. Okay, so we want to find Px. We know the acceleration is 0, and you can go from there and solve it. Any other homework questions? Okay. All right, so the last topic in particle kinematics in 2D is circular motion. And we're going to break circular motion up into 2 categories. Yes. Did you make sense out of it? I guess you need a couple equations that I haven't given you yet, or no? Okay. So the two categories are uniform circular motion. That's circular motion while you're wearing a uniform, like if you're a policeman on like a playground carousel or something. That's not really what it means. That was a joke. Okay, uniform circular motion is circular motion with a constant speed. And then the other kind is just non-uniform circular motion, where the thing is either speeding up or slowing down. Obviously, in non-uniform circular motion, there's an acceleration. What about in uniform circular motion? Because you're turning, yes, exactly. So there's still acceleration even if the speed is constant. And think about it in terms of, think about the velocity direction and then the part of the acceleration parallel to the velocity and the acceleration perpendicular. If you have uniform circular motion, the only acceleration is perpendicular to the velocity because it's making you turn. If you don't have acceleration, you keep going wherever the direction you are going in a straight line with a constant speed, until some acceleration occurs. So here's the easiest way, I think, to make sense of circular motion. It's to think about it in that way, like we have been doing in lab. So first, the velocity vector. So the velocity vector is tangent to the circular path in the direction of motion. Then second, a parallel is, it can be two things. It's in the direction of the velocity. If the object is it speeding up or slowing down? Yes. Just kidding. That's not what I'm looking for. Why don't you scroll your mouth shut a little bit and listen? Thank you. Yes, in the direction of V if the thing is speeding up. Yep. And it's in the opposite direction of V, slowing down. Okay, so that's exactly the same as the way we've been talking about it in lab. There's one thing so when you're talking about circular motion, we use a new term for parallel part of the acceleration and for the perpendicular part of the acceleration. In circular motion, and only in circular motion, a parallel is called the tangential acceleration. So I'll write that as A-tan. A-tangential because if it's parallel to the velocity, it's, tangent to the circular path. That means exactly the same thing that A-parallel means when we're in non-circular motion, but this is what it's called here. And then third, A-perpendicular is toward the center of the circle. Toward the center of the circular path. And in circular motion, and only in circular motion, A-perpendicular is called the centripetal acceleration. That means towards the center. And we'll call that A-cen. Okay, so as an example, yes. So far there's nothing new that we haven't seen in stuff in lab. There's 2 new names for these things, that's all, but we haven't introduced anything that we haven't talked about before. What's going to be new is we're going to have ways to calculate these 2 things that we don't have in general, for like a general motion. So that's going to be the benefit here. You can think of that centripetal acceleration, by the way, as that's the acceleration that's required to make something move in a circle. Okay. If something's moving in a circle, there's a part of the acceleration pointing towards the center, and it has, we'll see, there's a specific equation to calculate it. It's the same all the time. All right, so let's say this object is moving in this circular path. And it's going around the circle this way. So counterclockwise. And we want to know if the object, so call that point A, if the object at A is speeding up, what's the total acceleration? And second, if the object at A is in uniform circular motion, what's A? And we're just talking about directions here. Okay, so for part A, here's the path. And the object's going around the path counterclockwise. Here's the point that we're interested in. What direction would the velocity be? Up. I don't remember what colors I usually make these. Let's call that blue. Okay, so there's the velocity vector. For part A, we're saying it's speeding up. So is there a tangential acceleration? Yeah. Correct. And what direction is it? It is straight up. Same direction as V, yep. So There's the tangential acceleration. Yeah, you know, we don't have to know, to do this part, we don't have to know what's, it could be attached to machinery that's, you know, like a, that's right, that's right. We don't care about that yet. We will pretty soon. Yeah. Right. That's right. That's right. Yep. Okay, and then is there centripetal acceleration? Heck yeah. Exactly, thank you. I was hoping you would say that. So this is centripetal acceleration. Without that, it wouldn't be moving in a circle. So what do we know about the direction of the total acceleration? Somewhere in between. Perfect. So the total acceleration is somewhere in here. Yes. We'll see that the centripetal acceleration only depends on the speed at that instant, actually. Okay. So the centripetal part doesn't have anything to do with whether it's speeding up or slowing down. It just has to do with whether it's turning. All the stuff about speeding up and slowing down shows up in the tangential acceleration. Yeah, so at every instant you have a new velocity, and so you have a bigger centripetal acceleration. And you know that from like, so if you're, yeah, imagine you're a planet. Okay, this is easier to imagine than that. So if you're in a car taking a tight turn in a big parking lot or something, and you're speeding up as you do it, yeah, so every instant you're going faster, and so there's more. And that acceleration, you feel like, that's the need for the centripetal acceleration to be pulling you that way. Okay, so part B. It's one of those directions. We don't know what, because we don't have any way yet to know the relative magnitude of the tangential and the centripetal. You know, as far as we know, if it's slowing down very little, then this vector is tiny. And this vector is big. And so the sum of those two is pretty close to just straight towards the center. So what would make the A tan really high and A center really low? Like, how would you do that versus A center really high? We'll see the equations pretty soon, so that'll tell the story. But intuitively, if the thing's moving really slowly, so at that instant it has a small speed, then the centripetal will be really low. But if it's speeding up a lot, so imagine something that's barely started to move, but it's speeding up really fast, but you're still early in the speeding up process. Oh, then there's no acentripetal. Then there's a small acentripetal, but a big atangential. And then in that case, we'd have a total acceleration that was closer to the direction of atangential. Yep. So he's going tangent to the
yes.
And always, yep. Yes. And it's just like, we haven't done this in a lab for a few weeks, I guess. We'll get back to it. But it's exactly the same thing that we did when we have some random curve and we say, okay, velocity has to be tangent to the curve. And then we decide which direction A parallel is. And then we decide which direction A perpendicular is. So we've done that stuff in lab once before, and we'll do it a ton more. We just give these different names if it's a circle. Okay, so what about the case where it's the same motion, but this time it's uniform circular motion. The velocity is still in this direction, What's atangential? Nothing. It's not speeding up or slowing down, so there's no atangential. Centripetal is still towards the center. And so in this case, what do we know about the total acceleration? In that exact direction, yep. We're not adding two vectors, so in this case, we know it has to be straight towards the center. So in uniform circular motion, total acceleration is always towards the center. In non-uniform, it's not towards the center, but there is a part going towards the center.
Oh, acceleration.
Right.
But it's still going to the outside, speeding up how fast.
Right. That's right. So the velocity is always tangent to the circle.
How could something acceleration be producing?
Okay, so the idea of something. So the way that wording suggests a mistake that's really easy to make, and everyone's going to make sometimes, sort of confusing acceleration for velocity. So the acceleration has, so think of it this way. The acceleration vector is the velocity at instant 2 minus the velocity at instant 1 divided by the change in time, right? It's a and it's a limit. Okay, so that's because the acceleration is the time derivative of velocity. Let's think about two instants and see how that works. So here's our instant 1. And here's our instant 2. Okay, and let's think about the velocities. Here we have, at instant 1, we have a velocity, just sort of exaggerated, a velocity like this, right, tangent to the circle. And at instant 2, we have a velocity like this. Right, this is V1, this is V2. And so V2 minus V1, which is what gives the acceleration its direction, if these two have the same magnitude, like if we're in uniform circular motion, then at V2 minus V1 is V2 plus negative V1 add those together, and that's the change in V. Okay, so this is V2, this is negative V1. And so the velocities are this and then this, but the acceleration is in the direction towards the center. That's how.
So if you put that up there, it would be pointing exactly towards the center of the circle. That D2 minus V1.
Mm-hmm. And here's another way to think about it, actually. This will probably make pretty good sense. So let me give you a position function of something in uniform circular motion. Let's imagine something going around. Yeah, so we'll just think about the circle. So this is like another way to imagine it. So let's say that the position vector as a function of time is equal to cosine t sine t. then the velocity is negative sine t cosine t. And the acceleration is negative cosine t, negative sine t. Okay, so we're talking about the unit circle where the coordinate system is like this. So what this says is whatever time you're at, the position function is a vector from the origin to the point in the circle. Okay? And the acceleration is the exact opposite vector. So a vector from the circle back to the center. So somewhere in those two examples is full understanding, inner peace. Yeah. Okay, so let's do one more. So let's do part C now. So we did A and B. So let's say if the object is at A and slowing down, what's the acceleration? Okay, so I'll just pause for. Okay, so in this case, there's the path. The velocity is tangent to the path. Slowing down, so the tangential acceleration is opposite the velocity. The centripetal acceleration is always towards the center. And so the range of possible accelerations is in this quadrant. Any questions? Okay, so now we're going to have to go from position, velocity, acceleration to a new way of representing things that's going to be useful sometimes. So I'll call this the angular representation of motion. And in 2D, you can think of, we're going to start with, okay, no. Let me give you sort of a table that shows like the relationships between these angular quantities and translational quantities like we're used to. You're going to see that there's angular equivalents of basically everything that we've done with translational motion. So the left column is translation. The right column is angular. With translation, we have the position vector. Call it P. The corresponding angular quantity, number 1, is angular position. And I'll call that theta. The second one Translational is velocity, the v vector. For angular, what do you think the angular equivalent of velocity is? It all follows a pretty easy pattern. Angular velocity, very good. And we'll call that lowercase omega. The third one in translation is acceleration. The a vector. For angular, it's the angular acceleration. And we'll call that one lowercase alpha. Goldfish. And then the relationships that hold for the translational quantities also hold for the angular quantities. So velocity is the time derivative of position. That's also true for angular position and angular velocity. Omega is the time derivative of theta dot. And then the acceleration vector is the time derivative of the velocity vector. Oh yeah, the dots, yeah. I will. Oh, I will. I'll never make that mistake again. So angular acceleration is equal to omega dot. No. Bless you. I think it's just a time saver because you use time derivatives so often, you know. You just don't want to write it all the time, but I didn't make that decision. Okay, so let's take a 10-minute break. And when you come back at 8:45, I'll start with angular position and define all these things. So if you have an object moving in a circular path, and let's say that that object is here at this instant, then draw a line from the center of the circular path to the object. And the angle between this reference line and the line that the object is on is our angular position theta. The units for angular position are radians. Does that mean that you have to have your calculators in radians? It probably, in this class, you are not going to have your calculators in radians, although actually it could mean that, so that question was sort of dumb. But, because we're not going to use sine and cosine of radians values. So you can keep your calculators in degrees, but these are represented in radians. Well, I think I give a lot of numbers in degrees. So notice that this represents a single instant. So you could represent theta as a function of time. And then if you have theta as a function of time, you can take the time derivatives. So now angular velocity and angular acceleration are just defined in terms of those derivatives. So angular velocity omega as a function of time is just equal to the time derivative of theta as a function of time. Mm-hmm. And so the units for angular velocity are radians over time, and the SI units are radians per second. The plus minus sign of omega gives the direction around the circle. Around the circular path. A positive omega means the object is moving counterclockwise around the circular path. And a negative omega means that it's moving clockwise. So notice that the sine of omega is enough for you to know the direction of V. And vice versa. For example, where did that come from? Okay. So for example, if you know that the velocity at this instant is in this direction, and you know that the object is moving counterclockwise, and so omega is positive. And if you know omega is negative, that means it's moving clockwise. And so if you're interested in the point here, and you know that the object is moving clockwise around the circle, you know the velocity is like that. Yes. Any questions about that? Yeah. And now the angular acceleration. Alpha, as a function of time, is the time derivative of omega as a function of time. And it's the second time derivative of theta as a function of time. Those are just like two separate examples. So what it's saying is, well, it depends. I mean, you have to know what instant you're talking about. But so say that we know that at this point on the circle, the velocity vector is to the left. Then we know that it's going counterclockwise, so we know omega is positive. And on the other hand, say that we know that omega is negative. Then we know it's going clockwise. And so if we're interested in the velocity at this point and we know it's going clockwise, we know the velocity has to be up. Okay. So either one of those is enough to know the direction of the other one. Yeah. The units, what do you think the units are? Yes, radians per, so it has to be radians per time squared, and then if it's SI units, it's radians per second squared. And there's a relationship between angular velocity and angular acceleration that's the same as translational velocity and acceleration. If the object is speeding up, then omega and alpha have, what's the relationship there? Have the same sign, yep. And if the object is slowing down, what's the relationship? Yep, then omega and alpha have to have opposite signs. And it turns out that there are equations to relate the translational quantities to the angular quantities. And so if you have one set, you can go to the other set. So relationships between translational, and angular. First, the speed, which I always write as a capital V, is equal to the absolute value of the radius of the circular path times the angular velocity. So that r is the radius of the circular path. The second one says that the magnitude of the centripetal acceleration. Have we used this yet in this class, the magnitude of a vector thing? That if you, the absolute value of a vector like this means the magnitude, that's the length of the vector. Okay, you've seen that somewhere before. And that one is equal to the absolute value of omega squared r. And if you can write it another way, if you substitute in this expression for the speed, it's also equal to the speed squared over r. And I guess with these squareds, we can, assuming that r is positive, we can forget about that. Yes? It is the length of the velocity vector. So you can think of the velocity vector as a combination of a magnitude, which is the speed, and a direction. Third question. The magnitude of the tangential acceleration is the absolute value of the radius times alpha. Okay, so these only give absolute values of the translational quantities. So say that you know, excuse me, say that you know the signs of omega and alpha and theta or whatever. Do we have enough information to figure out the full vectors of the acceleration and the velocity? Because, you know, notice these equations, they only give us magnitudes. Can we figure out what the full vectors are? Well, the thing is that, so these equations don't give it to us, but we can figure out the directions based on the fact that, well, we can go from omega to the velocity vector and back and forth. And we know the centripetal acceleration is always towards the center. And we know that the angular acceleration and the angular velocity have that speeding up, slowing down relationship. So yeah, this is enough information. So that and what we know about directions already. Is enough to go either way between the translational vectors and the angular quantities. Okay, so let's do an example. So let's say that this circular path has a radius of 0.1 meters. And we're interested in what's happening at this point here. We know at that instant, so when the object is at point A, they were given that omega is negative 20 radians per second, and alpha is positive 10 radians per second squared. What are the velocity vector and the acceleration vector? What? Well, first let's figure out the directions of all these different things. If the angular velocity is negative 20, is that object going clockwise or counterclockwise around the circle? Clockwise, so the velocity vector is that way, up. Is it speeding up or slowing down? Slowing down because omega and alpha have opposite signs. So which direction is the tangential part of the acceleration? Yep. So the tangential acceleration is like that. The centripetal, there's never any question about that. That's always just pointing straight towards the center. Okay, so now we can use the equations to figure out what the magnitudes of those are. The speed, which is the magnitude of the velocity vector, is equal to the absolute value of omega times r. So that's 20 times 0.1 or 2 meters per second. And so what's the velocity vector? Well, it's, so for the velocity, we figured out that the direction is based on the fact that that's moving clockwise. So if the, yeah, so 0, positive 2. Any questions about that? And now for the tangential acceleration, well, what order did I go? Centripetal. For the magnitude of the centripetal acceleration, that's v squared over r or omega squared r, whichever one you want to use. So omega squared r is 20 squared times 0.1. No, if the, so it works the same way as velocity and acceleration. It's speeding up if omega and alpha have the same sign. And it's slowing down if they have opposite signs. Okay, so we know that the magnitude of the tangential acceleration is 40. It's down, so it's in the negative y direction. I'm sorry, I'm doing the wrong one. We're doing the centripetal acceleration. The centripetal acceleration is towards the center. That's the positive x direction. So the centripetal acceleration vector is 40, 0 meters per second squared. And now we can do the tangential. The tangential acceleration is the absolute value of alpha times r. So that's 10 times 0.1, or 1 meter per second squared. We know that that's in the negative y direction. So the tangential acceleration is 0, 1. Yeah. Zero, negative 1. Okay, so now we have the centripetal and the tangential. How do we get the total acceleration? Just add them together. Yep. So the total acceleration is the centripetal plus the tangential. That's 40, 0 plus 0, negative 1. How do you mean? Oh, I see what you mean. Yes. So, yeah, well, so if you're trying to, this is just like those vector calculations. We know that vectors don't have a location. They only have a magnitude and a direction. So to come up with the components for this vector, it's a vector in that direction. You take the tail of that vector, put it at the origin of wherever the coordinate system is. I mean, you can think about it that way in this case. That's not really the origin. I didn't specify an origin, but for coming up with the components of that vector, yeah, you can imagine the origin being at the tail of the vector. Okay. Yes.
So it doesn't necessarily have to be like at a point where the tangential and normal line are horizontal and vertical, right? It can be anywhere on the circle, so you have to multiply by the same. Like
yes, that's right. That's right. Yeah, if I had said, it would have been sort of a pain if I would have said calculate it at this point here and give you some angle. But you do these magnitudes just the same, and then you have to use cosine and sine to figure out the directions of those vectors. Okay, let me give you a problem to work on. Okay, so let's say that well, what this equation says is all that we can calculate is the absolute value, and then we have to get the direction from other information. That's because we knew that since omega and alpha have opposite signs, it's slowing down. So the velocity and the tangential acceleration have to have opposite signs, opposite directions. Okay, so let's say there's this bar connected to like a hinge. and the bar has a length of 0.5 meters. And let's say it's moving with, at this instant, it has an angular velocity of 10 radians per second and an angular acceleration of 20 radians per second squared. And we want to calculate at this instant the acceleration of this point P. Okay, so notice that in any time that you have a rigid body rotating around a fixed point, every point on that rigid body is following a circular path. Okay? Because that's the rigid body makes a fixed radius between the hinge and the point. So this point P is moving in a circular path around that hinge. Okay. So go to the board, see if you can work through this. Ask me questions if you get stuck. But see if you can think through calculating the acceleration vector of that point P. Okay, so the circular path, the imaginary circular path is like this, where this is the hinge. Okay, it wouldn't be able to make that full circle because it would run into the ceiling or whatever, but at this instant, it's on this circular path. And we're looking at this point here. The angular velocity is counterclockwise. Yes. So the velocity is this way. The angular acceleration is in the same direction as the angular velocity, so the tangential acceleration is the same direction. The centripetal always does the same thing, just points right towards the center. We know that the magnitude of tangential acceleration is alpha r. So that is 10 times 0.5 and the magnitude of the centripetal acceleration is omega squared r. So that's 10 squared times 0.5, so 50. And so the tangential acceleration as a vector has a magnitude of 5 pointing in the positive x direction, so that's 50 meters per second squared. Yep. Thank you. I just put the wrong number in there, like a stupid idiot. Okay, so then the vector is 10, 0. The centripetal acceleration vector is in the positive y direction, so that's 0, 50. And so the total acceleration is 10, 0 plus 0, 50. So 10 for the x, 50 for the y, meters per second squared. Any questions about that? Okay, let's stop there. I'll see you. Okay, so I have office hours at Jefferson tomorrow at 2:45 in the media center, and I'll see you there or Friday.
Oh.
Mm-hmm.